Good morning, everyone out there in this beautiful September. Today, on our Warner Orthopedics Wellness / the Well Theory webinar, I'm going to talk about cholesterol / the healing soul. You may be wondering to yourself, why would an orthopedic surgeon care about cholesterol? That doesn't make any sense to me. It does not compute. Well, I have a lot of patients who have a lot of pain and orthopedic conditions, and lo and behold, most of them are on statins. Then I started noticing, all of the stuff about metabolic health that we've talked about ad nauseum and should continue to talk about. And I also noticed that a lot of the people on statins felt like they had muscle pain, they felt like they had brain fog, et cetera, et cetera. So basically, I learned everything I could about statins and then cholesterol, which of course parlays into my whole theory that you are what you eat, which is really not my theory, obviously. But nutrition matters so much to how your body feels and how your brain works. And of course, your serum cholesterol levels plays into that. So effectively, if you're going to be a good doctor or really help people to the best of your degree, you really kind of have to learn everything you can all the time. And this is what I've learned about cholesterol since medical school. It's going to be basic. So if there's any people out there that are lipid people, don't get too mad at me. I'm just going to break it down the way I know best to teach people that want to learn about it and just want to understand more. When you go to the doctors, one of the basic things they check, and now maybe you'll just have a baseline understanding of that lab value and what it really means. All right. Hold on a minute. Let's check audio. We're checking our audio. Check the audio one more time. Are you talking to me?
No. One person said they were having trouble, but I don't see why. Don't touch it.
Somebody out there said they're having trouble with audio, so we're.
Anyone else?
Is anybody? If you're having trouble with audio, can you let us know? Well, if you couldn't hear me, how could you know to do that? Seems to be a recurring issue. Producer?
You're loud and clear.
Okay.
Kim is just, maybe she help him. Maybe you check her internet.
Kim, perhaps check your internet. Nobody else seems to be having trouble with the volume, so we're going to start. But remember, it's recorded and you can watch it later. That's me, Dr. Warner. I'm an orthopedic surgeon in Baton Rouge, but also founder of the Well Theory and also founder of the Healing Soul. I teach for LSU Ortho, and I'm just very interested in nutrition and how it plays into how you feel and how you perform. Okay, cholesterol, what is it actually? These are little pictures of it. They make me think of caterpillars, but that's actually the 3D molecular rendering of cholesterol, if you can see that. It is broken down into things like LDL and HDL, but really particles, okay? So particle count is what matters, and I'm going to explain that later. Why do we even have cholesterol? Well, we use it to make hormones, all of the sterile hormones. So think testosterone, estrogen, all those kind of things. Also vitamin D starts with cholesterol. Most importantly, cholesterol is in every single cell membrane, and phospholipids are in every single cell membrane. And without cholesterol, we would not be here. I would not be talking to you. My entire body is built of cholesterol because every circular cell has a lipid bilayer. I'm going to explain that next. And cholesterol is integral. And then, of course, cholesterol is needed for phospholipid transport and to move fat around the body. The particles are, okay? So why do we care about LDL? We're going to talk about that. Why is it so important? What should your numbers be and why? And then why do you care what your numbers are? Okay, so cholesterol, this is a lipid bilayer, both of these images, okay? The lipid bilayer is what the cell membrane is made of. Think of every cell almost like a water balloon. Inside the water balloon, the water is the cytoplasm where all the organelles and the DNA and the nucleus, everything's kind of hanging out. And then the water balloon itself, the rubber is the cell membrane, right? So in the human body, it's a lipid bilayer. So the outside can bind with water, but the inside's fat and can only bind to fat. So you have to have the two fats touching, and then the outer layer can combine with water-based molecules, and so that works for things inside the cell and outside the cell. It's kind of ingenious if you think about it. 25% of all of the cholesterol in your body is, guess where? In your brain. Super important for brain function. That's its own thing and its own metabolism. We're not really going to get into that, but I just want you to know cholesterol is quite important for cognition. It is the precursor for hormones. We just talked about that. And it's crucial for the formation of myelin and dendrites, so nerve function, okay? So the insulation on nerves. And then just remember, we talked about this talks ago, carbon is the basis for life, and all of life is a carbon cycle. So all molecules with carbon are super important for existence. And cholesterol is one of those, but you don't really use it for energy ever. Okay, so cholesterol being so important to cell membranes, sterile function, communications, phospholipid movement, and the brain, it's so important that every single cell in your body can make its own cholesterol. Think about that. We have the ability to manufacture cholesterol in every single cell. That's kind of amazing and also tells you how important it is. You also have the ability to absorb it from food should you need to. And it's a very tightly regulated system. This is an image of a cholesterol crystal. This is what happens when you get too much cholesterol in a cell. It'll crystallize and destroy the cell. If you have too little cholesterol, the cell will not function. So much like everything in the human body, balance is key. You can't have too much, you can't have too little. It's a Goldilocks situation. So you don't want crystal, like precipitation of cholesterol within your cells, obviously. But what matters for you and me in terms of heart disease are the particles, the lipoproteins. So the way that cholesterol is moved around the body, and that involves protein plus fat or cholesterol in a single structure. Okay, so, okay, great. I know what cholesterol is. I know I don't want it to crystallize in my cells, but really, why do I really care about cholesterol? 1/4 of all deaths in the Western modern world is because of heart attacks or some type of atherosclerosis related disease. 25%, 1 in 4 people is going to die from this, unnecessarily, really. Heart attacks were only even recognized as a clinical entity just about 100 years ago. That's astounding if you think about it. 50 years ago or so, they became an epidemic where now it's like 25% of deaths, okay? Eventually, we figured out that the control of LDL, low-density lipoproteins, is linked to fewer cardiovascular deaths, fewer cardiovascular problems, et cetera. It was controversial for a while, and there's still a lot of controversy I hear here and there, and you read different things, and it gets confusing. But I think it's pretty much considered fact by most people today that if you control your LDL level for a number of years, you have less risk of damaging heart disease. These are pictures of the particles. I'm going to talk about those a little bit more. This, and we'll talk about this later too, that is a cholesterol crystal. It looks like, I don't know, a piece of toffee or something, sitting inside of a macrophage foam cell. That's actually the disease entity that causes atherosclerosis. So the LDL particle gets into the blood vessel, macrophages gobble it up, the cholesterol crystallizes in there, gets oxidized, or it's oxidized before it gets in there, and then it becomes this inflammatory disaster of a mess that builds up into a pus ball, basically inside of the artery wall, and then that becomes calcified. And that is atherosclerosis. So again, cholesterol is in every cell. We make it. It's super duper important. It is the lipid bilayer, the cell membrane. Without it, nothing's going to work. It's needed to make the membrane fluid, to make it compressible, so it's not just stiff and rigid like a golf ball. It's going to be more like, you know, an inflated volleyball, I guess, in terms of compressibility. It helps with some water penetration or fluid management. It helps regulate the thickness of the cell membrane, and then it gives it its intrinsic curvature because the way the molecule of cholesterol is formed. And then there's a reservoir of cholesterol, should you need it, floating around in your blood. So the body has a way to have a supply. If your cells aren't able to make enough that they need, they have a supply ready to go that they can pull in and use. And that's the reservoir or the pool of cholesterol that's in your blood. That's what's getting measured when you go to the doctor's office. Those are pictures of cholesterol being pulled into cells. All right. So the function, again, fat is an essential component of your cell membrane, i.e. cholesterol and phospholipids specifically. the lipid bilayer. The membrane has to have structure and strength. So saturated fatty acids and cholesterol are in there. And then, of course, some polyunsaturated fatty acids like omega-6s and omega-3s, all combine to form the cell membrane. It needs to be flexible enough to let receptors be there. And we've talked about receptors in other talks. The receptors are like basically gateways in the cell membrane that when a ligand or a key, which is usually a protein, attaches to the receptor will change and let certain things function in the cell. So if your membrane's not flexible enough, that's not going to work well. Similarly, there are channels or just pores, like little holes that let ions in and out and electrolytes, things like that. None of this works well unless you have the correct configuration of the cell membrane. And then cholesterol is especially important for forming what are called lipid rafts, which there's a picture of it here. And these lipid rafts formed by the cholesterol are areas of high functioning where like a lot of the receptors congregate and work better. So cholesterol is super duper important to your cell membrane. This is a cholesterol raft where the darker color phospholipids are indicating that you've got some cholesterol hanging out there. So how is it water soluble, lipid soluble? What does that mean? So there's a polar end of a molecule that interacts with hydrophilic phospholipids. A phospholipid is a lipid attached to a phosphate group, okay? Now, one end is going to be water soluble, one end only likes fat. It's like when you drop oil into water, the oil is going to form globules that you can see. It does not dissolve in the water because oil is nonpolar, water is polar. Cholesterol also has ring structure. So the molecular structure is sort of a group of rings with some tails. And that maintains the flexibility of the membrane because the rings don't allow too much compression, I guess, and allows it to be still flexible even as temperature drops, okay? That's important. As you get colder and cooler, you're still going to maintain flexibility because of this cholesterol molecule. And then, of course, the lipid rafts that allow certain proteins and channels and stuff to function better. So the polarity is important. The creation of cholesterol, it actually starts with a 2-carbon structure you may have heard us talk about before when we talk about the Krebs cycle or how you convert food to energy, the electron transport chain. It starts with a molecule called acetyl-CoA. That's a 2-carbon structure, and then it gets eventually converted to a 27-carbon structure or cholesterol. It's about 30 to 37 steps, I can't remember which. It's many steps in this chemical reaction. You end up with 4 hydrocarbon rings, and a hydroxyl group and a hydrocarbon tail. And that's all cholesterol is. It's just a bunch of carbon glommed together in a certain configuration. Okay? So the hydrocarbon tail in the central ring are nonpolar. What does that mean? They like lipid. And then because they're lipophilic and not water soluble, but your body still needs a way to transport fat around and transport the phospholipids around where they're needed in the cholesterol for the cell membrane or whatever function, your body figured out a way that it can mix with water because your serum's effectively water. So rather than having globs of fat floating around like you dropped oil in water, it gets packaged into a polar protein molecule that lets it solubilize or lets it mix with water, okay? So the hydrocarbon tail's nonpolar, doesn't mix with water, so it has to be packaged so that it can be carried through water. More pictures of the cholesterol ring. And then you've got a picture on the bottom right of ApoB around triglycerides, phospholipids, and cholesterol, which is your LDL. Okay, so this is just showing you that when you're fasted, certain things happen. When you're fed, certain things happen. So when you're fasted, obviously, let's say you're fasted for a long time period, you're going to want to burn fat. Well, the fat has to get to the cells somehow. It's pulled out of adipose tissue or wherever it's being stored, and it's traveled to where it's needed, let's say muscle or brain, by way of these packaged molecules of fat, okay? You can go to the next slide. That's probably hard to see. So this is why you have an LDL particle. I don't know if you've heard a physician say particle, but LDL cholesterol is actually not a very accurate measure of your risk of heart disease. Really, you need to be measuring the particles or the ApoBs. And that's because this is how they're traversed through the water or through your blood. So again, fat not soluble in water, fat's made in the liver or absorbed in the intestine, right? Lipids have to get to the cells somehow. really mostly the phospholipids. That's the important thing. So the body really needs the phospholipids that are being traveled around. So the way the body does it, it creates a sphere with the outside of the sphere being water soluble and the inside being fat soluble. All the fat's packed inside, the ApoB is on the outside, that can dissolve into water, it can be traveled around. And then the ApoB, which is ApoB 100 on LDL cells, will actually be able to communicate with certain receptors on cell walls and be sucked in and out as needed. It's pretty ingenious, but like with anything else in the human body, if the balance is off, that ingenuity becomes a problem. So your ApoB communicates with the cells, and when the cells need a phospholipid or whatever, they'll pull it in, and then, you know, the next metabolism will happen that lets the cholesterol be integrated into the cell membrane.
You talked about lipoprotein A.
I didn't talk about it yet.
You're going to?
I'll mention lipoprotein A. Okay. So the spherical shape is important. So the spheres are a very efficient way to get fat through the bloodstream without glomming up and getting stuck on everything, I guess. So these are discoidal particles, that's the top picture, that are made in the liver, get in the blood, and then a certain enzyme will convert cholesterol to a molecule called a cholesterol ester. That's the form that can actually be packaged, okay? And then the spheres form. It's actually lecithin cholesterol acyl transferase. Anytime you hear ACE, that is an enzyme. That's a protein that is changing one molecule to another. So it's enzymes are like catalyzers for reactions. So the apolipoproteins can activate the enzymes. It can act as keys to receptors or ligands, and they facilitate the absorption and the transport of fat. Apolipoprotein B100 is the most important one in terms of cardiac health for most of us. So just quickly about what I mean by polar. So all molecules bind together by transfer of electrons or movement of electrons from the outer rings of the cells. So some cells have more mobile electrons, some don't. A polar one has a electrical dipole moment, meaning one side's negative, one side's positive. So water, the positives go to the H or the hydrogen and the negatives go to the oxygen. Because of that, it could be attracted to the opposite molecule, and that's what lets things dissolve. If a molecule doesn't have a more negative area or more positive area, it's not going to dissolve with anything. So everything, as we've talked about before, comes down to electricity and the movement of charge in the universe and the human body too. And this is just one example of it. So the polar molecules are gonna bind with H2O. Non-polar ones will not. Next slide. It's not working.
Just point it a little bit. Not
This one? You want me to put it higher? Is that better?
Oh, that one wasn't the one where I wanted.
Oh my God.
Put it on the coat.
Yes, ma'am. Hello? Now I look really cheesy. Okay. So in micelle, it's the spherical, you may have heard the term micelle, that is the spherical fatty structure that forms by the grouping or aggregation of surfactant molecules. So in water, the hydrophobic tails face inward, that's the fat. Hydrophobic, afraid of water. And then the hydrophilic, loves water, face outward. That's all that these lipoprotein particles are. It's just a simple way to get fat from the intestines and liver to where it's needed, or from adipose tissue to where it's needed, or excess fat to the adipose tissue. And then, of course, that's your lipid bilayer on the bottom. So these transportation spheres are pretty cool. There's a whole bunch of them. I'm going to go through them real quick in a slide coming up. But this is the primary, the VLDL, the very low density lipoprotein, which is on the continuum of density of these particles, has a ton of triglycerides, or like the actual fat sitting in it, okay? And then as the triglycerides are pulled out, the relative ratio of triglycerides to cholesterol changes, the particle becomes more and more dense. And then when you get particles that are primarily apoproteins, those are very high density, which we'll talk about that too. Here's your listing of different particles. So the chylomicrons are the fattiest. This is what's formed when you absorb fat in your diet and gets into the lymph system and then is transported around the body. There is an APO capital A on the chylomicron. There's also an apolipoprotein B48. All that means is 48% the size of the B100. And then there's a C and an E. As triglycerides or fat are pulled out of the chylomicron and stored in adipose tissue or stored wherever they're needed or used, it becomes a very low density lipoprotein, okay? That has an ApoB100. And it's pretty atherogenic, but not nearly in terms of volume of numbers of particles as important as LDL. There's a little transition stage between the very low density lipoprotein and the low density lipoprotein, and that is the intermediate density lipoprotein. That has a super short half-life, so we don't really talk about it that much. The LDL is when even more triglycerides are pulled out of the VLDL. And then so the ratio is a little bit higher on the cholesterol to triglyceride side. And of course, the protein count is a little bit higher. And then the HDL, the high density lipoprotein, is the densest of all. So the most protein filled and the least amount of fat and cholesterol. That has an apoprotein capital A receptor as well. HDL, think of it like the garbage truck of your body. It's going to pull out whatever's not needed and try to get it to the liver and the intestines to dump it out and excrete it. So the efflux of fat in your system is the most important thing. So as you take stuff in and as you make it, because remember I told you every cell can make cholesterol, there has to be a way to get rid of excessive amounts of this stuff, because remember I told you the body likes a balance. HDL is integral to that getting rid of it kind of stuff. So the chylomicrons are 90% triglycerides. VLDLs are 60% triglycerides, LDLs are 50% triglycerides, and HDL is really only about 5% triglycerides. So you can see the fat content just diminishes as these things get denser and denser and denser. Remember, lipoprotein just means fat and protein. So it's just the fat with the apo, whatever the apo is on it. So how do we figure out that LDLs even matters? Why? How do we know this? What's the history? In the 19th century, some German scientists figured out that plaques on the aorta that they found in cadavers and things like that was a type of cholesterol. They named it athero, which in there meant gruel. So it looked like, I guess, oatmeal, which is kind of nasty if you think about it. In 1910, Windhouse found that these aortic plaques, these little pockets of gruel, held about 25 times the amount of cholesterol as a normal aorta without these plaques, okay? So they're starting to figure out there's something going on with this lining of these aortas that seems to be related to cholesterol. Now, at this time, pathologists thought that these plaques were 100% fatal, and if you had them, you were going to die no matter what. So because of that, any other type of chest pain or non-fatal kind of cardiac event, they thought had to do with something else completely different. Because at the time, they thought if you had plaque on your artery, you were going to die no matter what. They did not understand there was a continuum of this disease process. So a causal agent like cholesterol wasn't even considered at the time. It was actually just thought to be an inevitable consequence of aging, as has been the scourge of most medical thought for a long time about a lot of our problems. Everybody just chalked it up to time. But they're starting to get a window into what a plaque is, okay? So in 1856, Virchow, and there's something called the Virchow's triad, which is what we look at as physicians to kind of predict risk of like blood vein clots and things like that. Virchow had what's called the insudation theory, which really was kind of a harbinger of the lipid heart theory that came much later. So even in 1856, we kind of knew something was going on. In 1916, interestingly, this Dr. de Langen, who was one of the Dutch guys that was colonizing Indonesia at the time, he figured out that the cholesterol was much lower in the native Indonesian population than in the Dutch colonists. He figured out somehow that this was maybe diet related. So he took 5 Indonesians, put them on the Dutch diet at the time, and their cholesterol rose almost 30% just in 3 months of just switching their diet from the Indonesian native diet to the Dutch diet. Then he also noted that some Indonesians that had moved to the Netherlands as part of the cross-population movement in the colonies at the time had a tremendous rise in their cholesterol levels. Why? Because they got on the Dutch diet. He published this and wrote this, but was completely ignored information. So in 1916, we knew this was going on, but nobody cared. They just ignored it. I don't know why. That's the way medicine is. There's a lot of groupthink. In 1913, Anichkow at the Russian Military Institute, so a lot of what we know today, believe it or not, has come out of medical work done in Russia at their military institutes. In 1913, this young guy fed pure cholesterol to rabbits, and then he noticed that the rabbits developed severe atherosclerosis pretty quickly, being fed pure cholesterol. So he knew that dietary cholesterol was the culprit of this plaquing, or the gruel on the lining of the arteries, that was associated with heart death. Didn't publish this in English until 1933. In 1919, Herrick used an EKG and electrocardiogram, you probably all had one of those, and showed that the pattern of the electrical activity of the heart did change in patients that were having chest pain. Remember I told you before they thought chest pain was something else entirely different than plaquing on arteries in the heart? Now, because of this electrical study this guy did in 1919, they could connect the two. Now they know chest pain is a heart issue. So you see, science just kind of like builds on itself, and there's just incremental improvements over time. Nobody knows what you don't know, right? The more you know, the more you realize you don't know, right? So the rabbit model was actually discounted for a long time, and I still hear this discounting today. Oh, they're herbivores, they never eat cholesterol, so that's an invalid study. That's the primary criticism of this rabbit model, okay? The other criticism is they did the same experiment in dogs and rats, but the dogs and rats never got the atherosclerosis the rabbits got. Well, it took them forever to figure this out, but about 33 years later, Steiner and Kendall proved that the difference is dogs and rats have a better efflux system. They were able to excrete or poop out the excess cholesterol much quicker than rabbits. So remember I told you that efflux, or the garbage truck system, is very, very important? It is. The rabbits have no garbage truck system. So they built up plaquing very, very quickly if they ate any of this stuff. The dogs and the rats were able to poop it out, so they were safer for a much longer time. Efflux was found to be hugely important. In the 1940s, in this country, 95% of our population had cholesterol values over 280. Think about that. I know you know what your doctors told you got to be under 200, right? Normal back then was 280, okay? Normal. We've talked about this before too. Heart attacks happen in people with cholesterol, total cholesterol levels, 200 to 280 milligrams per deciliter. That meant at the time in the 1940s, heart attacks were happening in normal people, normal in terms of their cholesterol levels. Therefore, it couldn't be cholesterol. That could not be the causative agent of a heart attack because everybody was normal. So nobody looked at it. This is one of the problems when we have biomarkers that are based on a normal, based on the existing population. Think about that next time you go get your blood levels checked. You really need to know what is the optimal human level of X, Y, or Z, not what's normal in my country at this time, because it could be very skewed, as it was in the 1940s, which sort of slowed down our knowledge base. 1933, Schonheimer fed some mice a cholesterol-free diet, and then he found that internally the cholesterol levels increased in the mice. So the less cholesterol they ate, the more they were making of their own. Then he fed them cholesterol, and then suddenly they made less on their own inside. This is the first time we had a valid description of what's called now an end product feedback inhibition loop. So in other words, the body has a way to know how much cholesterol there is in a cell, and it'll shut down certain things to make sure that that balance is maintained. So it is inhibited in a feedback mechanism by the product, okay? And this was the first time they actually really proved it. And then when certain proteins important in that process were knocked out with genetically modified mice, a fatty liver would result. So we now knew that we could make and also absorb cholesterol, and homeostasis was normally achieved in the body. It was normally balanced, or should be normally balanced. In 1938, this disease, which is a genetic called familial hypercholesterolemia, was discovered. All that means is familial, it's in families. Hyper, too much, cholesterol, emia, blood. Family-based, too much cholesterol in their blood. Mueller, another German scientist, found that it was an autosomal dominant trait, meaning it was passed down directly. Like it wasn't recessive like blue eyes, it was more like brown eyes. And families were found with very, very, very high cholesterol levels. Particularly, he was looking at 17 Norwegian families, and it was in this one area in Norway where there was a certain amount of inbreeding. And so these genetic problems were more prevalent. And he proved that xanthomatosis was a causative agent of heart disease. Xanthomatosis is shown in this diagram. I see this in my clinic periodically. You'll see people with like little clusters of fat, like under the skin, like on the eyelid, the upper eyelid, sometimes on the Achilles tendon, sometimes on the elbows, sometimes on the digits, like extensor areas where there's like stretching and extension, and sometimes even in the eye. So people with xanthomatosis, that's what that is, were found to have very high rates of heart disease. Turns out it's just cholesterol crystallizing wherever it can, associated with a 20-fold chance of a heart attack by the time you're in middle age. So these are the people that are having heart attacks in their 50s, 40s, whatever. Now, here in America, 1949, the National Institutes of Health Heart Institute was formed during this time, and it had more money than any of the schools around. So at this time, the NIH was more funded than all of the universities. And it was able to offer draft deferments because it was a government entity. So it was able to keep people from having to serve their country. And in this way, they were able to recruit a lot more good scientists. Like, it was more competitive, the NIH. This is why the NIH research dynasty and so-called Building 3, which was a heart institute, became a pipeline of Nobel laureates, because they were basically able to have this very shiny object of a draft deferment and get everyone in the country trying to get that, or at least all the people that didn't want to serve. In the 1950s, they finally figured out that HMG-CoA is an important step in the pathway of making cholesterol. This may sound familiar to you if you're on a statin. Remember, you start with the 2-carbon molecule acetyl-CoA, and it goes through 30 to 37 steps to become the 27-carbon ring structure cholesterol, and every cell can do it. The rate-limiting step has to do with this particular molecule, HMG-CoA, which is 3-hydroxy-3-methylglutarol coenzyme A. Clearly, that's why we all say HMG-CoA. HMG-CoA reductase. Remember, I already told you what ACE is. So this is an enzyme that catalyzes this particular transformation in that chemical reaction. That was found to be the rate-controlling enzyme in cholesterol synthesis inside the cell. That's the bottleneck. So HMG-CoA reductase will convert molecules of acetyl-CoA into mevalonic acid, which is one of the next steps in the pathway. And then it just keeps moving on and on and on. Thank you. So this is done in an organelle in your cell inside the sphere, inside the cell membrane, called the endoplasmic reticulum. Okay, and that's going to be important later. So remember, proteins are made in the endoplasmic reticulum, or these chemical reactions are happening there. And it's managed by the feedback loop. So your body has this ingenious way to sense how much cholesterol is happening, and we're not going to get into that in this talk, but it's pretty cool. And HMG-CoA is either upregulated or downregulated, and then LDL receptors on the surface of the cell that pull cholesterol in are either upregulated or downregulated based on how much cholesterol your cell needs. It's basic supply and demand, pure economics here. So as the supply goes up, the demand goes down, or if the supply goes down, the demand for the cell goes up, and it will find a way to get the cholesterol it needs. In 1951, White and Gerther found the risk factors that were associated in people with heart attacks. So this was a lot of epidemiological work. Remember, we take all the stuff we know now for granted, but during this time period, this wasn't really known, and nobody had really put everything together. They looked at 100 people under the age of 40 and found that these are your risk factors to have a heart attack. If you're a guy, if you have high cholesterol, if you have high blood pressure, if you smoke, if you have a family history of it, or if you have a mesomorphic body, so like truncal obesity. Those are still risk factors. In 1953, Ansel Keys produced the famous 7-country study. If you've watched my talk on Mediterranean diet or anything to do with that, you know what I'm talking about. So in this study, he looked at 7 different countries, 16 cohorts, all that means is groups, of healthy men followed for 10 years. Okay, so they're all healthy in their country eating their normal diets. Japanese fishermen, on average, had a cholesterol of 165. Finnish foresters had a cholesterol of 270. Remember, that was normal in the 40s in the States, right? So did we. So the Finnish foresters are like slathering butter on top of fat, and the Japanese are eating eel and seaweed, right? So clearly they have a big difference. And there was a 13-fold rate of heart attacks in the Finnish versus the Japanese, and so on and so forth. So he found, looking at these different countries, based on the diet, that the rates of heart attacks were strongly correlated with the diet. Now, of course, correlation doesn't mean causation, but we're on to something here. High fat, especially trans fats, okay, that's a certain type of saturated fat, lead to high cholesterol and heart attacks. So he felt that the key was saturated fats. Now, at the same time, there's another scientist, Youngkin, who thought the key was sugar. Turns out they're both kind of right. Really, you should limit some saturated fats. You should limit trans fats for sure. And really, you need to limit added sugar because they're all causative in this whole cascade of events. But this was the start of the so-called lipid heart hypothesis. So now we're really starting to put it together. They also noticed that Japanese people that migrated from east to west, so like the Japanese that went from Japan to Hawaii, started to eat less health foods, started to have more heart attacks. Why? Because their diets changed. So again, more and more data is coming clear. So before we understood the densities, we only had total cholesterol. So a lot of the information in the studies in this time period, you couldn't really have a fundamental understanding of why heart attacks are happening because you could only measure total cholesterol. So a lot of our science really is dependent on the technology of the time. That's why it's so important to have good technology. So this guy, Goffman, he was a particle physicist. Then he decided to go into biology and medicine too. So he had 2 schools of thought in his head, which is always very important too. It's one of the reasons I try to keep an open mind and learn about different things like cholesterol, because I'm pretty sure it'll help me in ortho. This guy is a particle physicist, and he was a doctor, and he was able to work with the particle physicists and had this new measurement machine where they were able to actually differentiate the particle densities and the particle size. And he was able to find LDL and HDL, okay, and figured out that there was a difference and that the smaller particles, the LDLs, mattered the most. Plasma from heart attack victims had a lot of LDL and not much HDL. That was seen in the Framingham data. That's a group of people that were followed, I think, in Massachusetts for years and years and years. And it was profoundly correlated. Actually, the low HDL was more correlated with heart attacks than the high LDL. But that has to do with some methodology and some other issues. But importantly, we realized from some epidemiology studies that high LDL really, really matters. And now we knew about LDL because of this new machinery that this particle physicist was able to bring into the game. Now, Goldstein and Brown were able to bring even more knowledge to the game. So they were the ones that helped to figure out about this LDL receptor. So this receptor on the surface that pulls LDL in when needed. They had cultured fibroblasts, so these are just cells that grew in a petri dish. They were found to either make their own cholesterol, okay, or they collected it from surrounding fluids. The plasma that they had with the fibroblasts from people with familial hypercholesterolemia, so that genetic cholesterol problem, were unable to take in excess cholesterol from the surrounding petri dish. So there was an issue there. Remember, most of us can make it and absorb it. These cells from people with FH could only make it, they couldn't absorb it. You went up the slide, go back one. So this study that these guys did demonstrated and proved that homeostatic balance inside of your cells of making and absorbing as needed. They also found or showed and helped us all understand that the liver makes empty HDL and it also makes VLDL. So VLDL can come from a chylomicron having fat pulled out, or the liver makes it itself. And then they were also brought to us that LDL is a major lipoprotein that's bringing stuff around to us. This is a great image of an LDL receptor pulling in a molecule of LDL by attaching to the ApoB100 protein shell, okay? LDL uptake, all uptake means is the cells bringing it in, happens due to these receptors. They were discovered by Anderson, Goldstein, and Brown in 1977. At this point, LDL is hydrolyzed and cholesterol is then released and used for membrane synthesis, or the phospholipids are used, or the fats used, or whatever. The uptake of LDL, pulling it in by these receptors, is coordinated with the activity of the HMG-CoA reductase enzyme. So it's coordinated action. Again, supply, demand, very, very important. If you were found to have low cholesterol, or the cell felt like it didn't have enough cholesterol, it will produce more receptors, throw them out there to pull LDL in, or it upregulates HMG-CoA reductase activity, which means you're going to make more cholesterol, or it does both. If you have very high cholesterol, the opposite happens. And then we knew that the LDL receptors were linking to ApoB100. This is why particles matter more than total cholesterol. The ApoB100 is how the LDL is going to get in and out of cell membranes and into the endothelium and cause atherosclerosis. And also, the number of these particles are huge. So there are far more LDLs floating around than VLDLs and chylomicrons and whatever else. So remember, familial hypercholesterolemia, or FH, was discovered in 1938, but nobody knew why this was a problem. They just knew it existed. The reason wasn't discovered until around about 1974, when Goldstein wrote that it was probably a defect in the gene for the LDL receptor. And remember, the fibroblasts of the people from FH couldn't pull in the cholesterol from the surrounding Petri dish fluid. They figured out it was a defect. These people are unable to make a proper receptor to pull LDL in out of the serum. Therefore, their serum is always chock full of LDL. In 1985, they got the Nobel Prize for this, that the lack of LDL receptor activity is a sufficient cause for atherosclerosis. So just not having that little receptor, that little looks like a golf tee in the bottom picture, not being able to have that receptor is enough of a reason for your body to have atherosclerosis and put you at risk of heart disease. And that got a Nobel Prize. In 1968, these guys were part of the Clinical Associate Training Program at the NIH. This was a 2-year program approved by the federal government as federal service. So again, this is a way to exempt people from the draft. 9 Nobel laureates were created by this program between 1964 and 1972. That's because competition was fierce among these high-level scientists to try to avoid the draft. I put this picture here because this was my dad flying his helicopter in Vietnam, and he was part of the Bat-21 rescue. My dad and thousands of others were not able to get into these draft deferment programs. I don't know if it's a good thing or a bad thing, but it's just an interesting historical fact that these guys got out of the draft, but then went on to win the Nobel Prize. So LDL in the liver, circulating low density lipoprotein cholesterol, that's what LDL-C is, picked up by the liver cells. LDL cell receptors are upregulated, and then it's all processed in the liver. The liver will make very low density lipoprotein, cholesterol, and apoproteins. So the liver actually makes the apos too, by the way. Packages them all up. It'll also make your HDL empties, send out the empty garbage trucks to go take care of business. LDL can be effluxed or passed out of the system from the liver as bile. Or LDL can be recycled and reused for whatever purpose. So the way we get rid of it is pooping it out as bile, or it's not absorbed and it's pooped out. That's the only way we can really get rid of cholesterol. And this is what a gallstone is. So cholelithiasis, or a gallstone, is either a bile deficiency or too much cholesterol in the bile, so it crystallizes. Remember, I showed you the pictures of crystallized cholesterol. That's what happens when you have too much cholesterol. It precipitates. It's like if you put too much salt in water, you'll just start to see it, I guess. So you have to have a proper balance of your bile salts, your cholesterol, and your phospholipids. Otherwise, it crystallizes and you get these stones. Bile acid resins block bile resorption. So this is your cholestyramine, cholestyramine, cholestyramine. These drugs block the ability to reabsorb bile, and then you basically poop it out. Cholesterol absorption inhibitors, so blocking cholesterol absorption like ezetimibe, and I think that's Zetia, if I'm thinking of the proper brand name. Those are gallstones in the bottom right. So quick summary of what you learned so far. You eat food, cholesterol is absorbed into the intestine, made into a chylomicron, 90% triglyceride. The fat and phospholipids are delivered to the tissue. Some of the fat's pulled off. You're left with a remnant, a VLDL, a very low density. Fat's either sent to the tissues, sent back to the liver, or it's stored in adipose. You're left with LDL, a remnant of the VLDL. It's a low density lipo. Low density lipo brings cholesterol to the tissues or back to the liver to be effluxed or recycled. HDL, high density lipoprotein, will pick up any excess cholesterol from the tissues, the serum, from other LDL particles actually, and will take it back to the liver to either be recycled or effluxed. So HDL also transfers and moves around apoproteins as needed. So HDL is really sort of like integral to the maintenance of your cholesterol system. Okay. So, do you want to do? Oh, anybody have any questions so far? I'm going to keep going. You can ask questions at the end too. So what's the problem? When you have too much LDL, specifically LDL particles attached to apolipoprotein B100, or that's redundant, attached to ApoB100, the LDL can penetrate or get pulled into the endothelium, which is the lining of your blood vessels, and it is retained there. It'll get oxidized, okay, which is bad. We know that, oxidative stress. And then macrophages will come in to scavenge that inflammatory particle. Foam cells form, think of pus, and then cytokines, inflammatory proteins come in to try to take care of that. And then eventually you get this ball of foam cells and you have a plaque. Eventually, that'll get stabilized by the deposition of calcium. That's when you can start seeing it on a cardiac calcium score or on, different ways to image vessels. The importance that inflammation plays in this whole process was not really noticed until the 80s. So there were working theories on why plaque formed prior to this. In 1976, Ross and Glomset thought it was just damage to the vessel walls from things like hypertension, we'll say, or like trauma. And the damage to the vessel wall will allow a foam cell to form. In 1981, these guys in La Jolla thought that tumors formed inside of the cell wall of the blood vessel, specifically formed of white blood cells, so a white blood cell tumor. They thought that was the inciting event. And then in the 80s, we started to realize how important inflammation was. And we've talked about this a lot. An oxidized LDL or an inflamed LDL is not a good LDL. You don't really want that. That definitely contributes to this problem. And that's because they're modified by free radicals because of things like hyperglycemia, inflammation, et cetera. This is why your high sensitivity CRP level is a very good marker of your risk of cardiovascular disease. This is a picture of a foam cell. I showed it to you before, but I think now it might make more sense to you. So that cholesterol molecule has been oxidized, and it's got all of this macrophage stuff, and it's becoming inflamed. Okay, so we talked about how the VLDL is secreted from the liver, the triglycerides are pulled out, they're either sent to your fat cells and stored, or your muscle uses them or whatever. Any excess LDL-P or LDL particle in your blood should be pulled out to keep the balance right by the LDL receptors. If it doesn't, it floats around until it gets absorbed into the endothelium. That's when it becomes a problem. So the real problem is how much LDL you have in your blood and for how long. It's like a cumulative effect. So this is why it's important to get control of this as early as possible. So in 1976, this gentleman of Endo Pharmaceutical, his name was Endo, that was his last name, found the first HMG-CoA reductase inhibitor. He discovered it. They were working on how to inhibit, like how to make good antimicrobials, and they figured out that if they could control cholesterol synthesis, they could kill bacteria, basically. And then they eventually figured out they could use it in humans. But they found that when you suppress the making of cholesterol, the cell, what? Oh, I feel like you're laughing at me. When you suppress the manufacturing of cholesterol, the cell makes more receptors. Remember, I told you that before. The body's always going to keep a balance of cholesterol. So if you can't make enough, it's going to pull more in from the blood. This guy found the first statin. He called it compactin. And he found that it inhibited the activity of the HMG-CoA reductase inhibitor. It inhibited the HMG-CoA reductase enzyme. It took him 2 years and 6,000 experiments to figure this out, to find a way to block cholesterol synthesis. Initially, he tested it in rats. It didn't really work. Then he realized that his methodology wasn't quite right for that model, kept at it, proved it. And then there was this huge competition with Merck over a number of years to be the first one to bring it to market, to lower it in humans. Because at this point, we kind of knew it mattered. I just need a sip. I'm just talking too much. Yeah, I'm just getting over a bit of a head cold, sorry. So there was a competition in Merck. Interestingly, Endo backed off and ended up not being first to market because in the process of their experimentation, they noticed that in the rats they were looking at, the endoplasmic reticulum appeared to form tumors. So they thought that cancer was being formed by these drugs. It wasn't a tumor, it was just that the endoplasmic reticulum was working so hard to make more LDL receptors that it enlarged. So it was actually the normal natural feedback loop. It was actually working. But it was working so well it looked like a tumor. So they backed off, shut it down, and Merck won. Brown and Goldstein, the guys I talked to you about before, saw a paper by Endo in 1977, and they started working with him. And then in 1978, they had this joint publication. That's the title of the paper. And then this is when we really started to figure out how to help people drop their cholesterol with statins. And then this was that scandal, triparanol. I don't know if you heard about this. This was, this sort of held back the science for a long time. This drug was found to lower cholesterol in rats and dogs by up to a quarter, 25%. But it did it at a different level in the synthesis pathway. So it stopped a molecule called desmosterol from becoming cholesterol. Desmosterol, however, did not always show up in measurements of the day. So it was a skewed study, and then people taking this developed hair loss and cataracts, and some even got blind because of the cataracts. The company knew that these side effects were happening, or it was proven that they knew. They lost, and no other work was done for 20 years. So it's kind of a good thing that they found the scandal and stopped it, but it really scared corporations from moving on with this. And for 20 years, people kept dying of heart attacks. I had a little tickle in my throat. Okay, sorry about that. Tickling the old throat. All right. So statins, that's your plaque right there, right? So whenever you think about plaques, just remember this picture and you'll know how important it is to stop the plaques. Merck developed a molecule called mevinolin in 1981. The hypothesis was proven true. If we can stop the production of cholesterol in the cell, we can lower LDL particle count in the blood, and then we can reduce the risk of heart disease. So this was a good thing. This became Mevacor or lovastatin. So this was the first FDA-approved drug to lower LDL-C. It was actually approved before it was known if the outcomes changed at all, ironically. This is sort of similar to how some drugs for Alzheimer's have been approved because they reduce amyloid, even before we knew if amyloid reduction would help outcomes of Alzheimer's. Turns out they don't really. You got to get a little bit more esoteric. But the FDA allowed this based on the reduction of cholesterol alone because of all the work that had been done before this. In 1994, the 4S study was completed. This is a Scandinavian simvastatin survival study group, 4S's. It reduced heart attacks and prolonged life and reduced the risk of coronary events taking a statin, simvastatin, which was the first one on market, remember? Or no, sorry, that was lovastatin. So this was the feedback loop in action. Remember, supply, demand. When you take a statin, you're not making as much cholesterol, so your body makes more receptors and you pull it out of the blood. And then it gets transported to the liver eventually and hopefully effluxed out. And that's how you get rid of excess cholesterol.
Interesting how the liver is so connected to the process.
Yeah, the liver turns out to be hugely important in this whole process. The liver is making all of the APOs, the liver is making most of the VLDLs, and the liver is also involved in the recycling or the efflux. That's the average cholesterol level for humans. And then the blue one is going to be, so the x-axis, the bottom line is cholesterol levels. The top line is people. So in Asia, most people have low cholesterol. In America, most people have high cholesterol. And then in the bottom graph, it shows what that means. So high cholesterol, x-axis, coronary events, y-axis. As you get higher cholesterol on the x-axis, your number of coronary events increases, so you get higher on the y-axis. This is why we found the 7-country study results. Fewer problems in Asia because they had lower cholesterol levels, and this graph shows that beautifully. More problems in Western countries with terrible diets because of high cholesterol levels. Yeah, I think it was a decongestant. This is the 4S study showing you the effects of simvastatin, and they tested it versus placebo. LDL dropped by 1/3. Cardiovascular deaths dropped by 40%. Now, one of the criticisms is of what? 40% of what? And then total cholesterol drops by 20%. For every 40 milligram per deciliter drop in your LDL cholesterol count, your vascular events drop by 1/5, 20%. Believe it or not, simvastatin is now sold over the counter in Europe because they consider it so important. This study was produced recently. I think it's sort of like a response to some people that don't really believe in the LDL concept or the LDL lipid theory. This guy, Ferenc, showed the cumulative risk of LDL over your lifetime and your heart disease risk. So basically, the longer you can keep your LDL-C levels lower or your LDL particle count, the better. And that's your bottom line. So your heart disease risk is 50% lower. And these are your statins. So based on your LDL count, you're either going to be on a high intensity, a moderate intensity, or a low intensity. and your doctor will pick that one based on whatever. And like how quickly they want to drop your LDL. We don't know that much about HDL relative to what we know about LDL. We used to think that it mattered more, and they did many studies, and different drugs attempted to go on market for this, but nothing was ever shown to reduce the risk of heart disease. So in other words, just changing the HDL level did not save lives like changing the LDL level did. This is your ApoA. So ApoA is on the HDL, and the ApoA will allow the HDL to function. So you need it, but the LDL is more important, turns out, overall in terms of epidemiology. So again, you're either going to poop it out or you're going to convert it. Your gut biome can convert some of your cholesterol and make it not absorbable. That helps. That's why having a good gut biome is important too. And then your HDL will move it around and take excess cholesterol off of LDL and take it to cells where it's needed, or take it to get it effluxed out. So in answer to the earlier question, your capital A1 levels do matter.
The lipoprotein A.
Yes, but there's a capital A and there's a lowercase a.
This lady's question was, she has a lipoprotein capital A to be checked, and it was high, but the doctor didn't know how to turn it down.
Yeah, I think maybe the little a is the bad one. The capital A is on HDL, you want that. The little a, it makes your LDL even more atherogenic. So you have indirect and direct efflux, or getting rid of cholesterol with your HDL and your digestive system, okay? HDL will take it back to the liver, go to bile, go to the gut, go to the bowel. Or HDL will take it to the liver, same thing, or to the intestine, same thing. So it's going to move it wherever it's needed to sort of get rid of it the most efficiently, if it needs to be gotten rid of. That's a great picture of a lipoprotein molecule showing you the kind of the spherical structure with the phospholipids that are water soluble on the outside, with the apoprotein that really makes them water soluble, and then the triglyceride and the fat inside. Triglycerides are your main storage form of energy. And then this is 3 fatty acids on a glycerol backbone, triglyceride. This is your storage form of energy. And then in very low, you pull it out of the chylomicron. It becomes a very low density lipoprotein, and it gets put into adipose tissue. And there's certain enzymes that are important in this process. Then it becomes your LDL. So it used to be thought that lowering triglycerides is not quite as effective in reducing heart disease as lowering the LDL. That may or may not still be true. I don't think we fully understand HDL enough to really say. But we do know that LDL particles are more atherogenic than just triglycerides. And again, ApoB100 matters the most. So really what you should be getting checked is your ApoB100 levels, or your ApoB. So to review the metabolism, that's your cholesterol molecule in the middle, and your different steroids around it. You see how similar they are. Cholesterol is mainly found in the cell membranes, regulating the rigidity, the fluidity, the functionality, and the permeability of the bilayer membrane. Also helps to bind transmembrane proteins and change their function. So you're not functioning unless you have cholesterol. Then cholesterol is important too, because if you modify cholesterol, you can form steroids. And then you can also form vitamin D, which is cholecalciferol. Cholesterol itself is never really used for energy in us. It's really used for structure and function. Okay, so we're going to review here 4 parts of the metabolism. You make it, you absorb it, you efflux it, you store it. Again, every cell can make cholesterol, none really metabolize it. Getting rid of it's hugely important. Okay, the biosynthesis of cholesterol, remember how many steps I told you was in that chemical reaction? Very tightly regulated, uses a lot of energy. Begins with your 2-molecule acetyl-CoA, which is in the Krebs cycle, converted by HMG-CoA reductase to mevalonate. That's the rate-limiting enzyme, so that's the bottleneck of the process. Then becomes squalene, then becomes linosterol, and then it'll pick one of two pathways. Bloch and Federer, I don't know how to say his name, got a Nobel Prize for describing one of these, and it'll end up as cholesterol. Every cell's doing this all the time. But then your liver's making it too, and your liver knows it needs to be sent out because your fat might need it, your muscles might need it, somebody's going to need it for energy, the fat, I mean. So it needs to be packaged up and move around. More importantly, the phospholipids need to be packaged up and move around to go into the cell membranes. And then the cholesterol is inserted into the cell membranes. It's strategic points for all those functions we talked about before, including those rafts. So you're going to have the chylomicrons. They're going to be converted to the VLDLs. And this shows you the map of the densities. So the really fat triglyceride-filled particles are going to be really buoyant and float to the top of a density chart, if you will. And then the HDL, mostly protein, far less triglyceride, remember 5%, that's going to go to the bottom. That's why we have these bizarre terms of high density, low density, intermediate density, very low density. Again, liver, very important. Your intestine absorbs it out of what you eat. That does happen with the Niemann-Pick type C1-like protein receptors. It's a mouthful, but that receptor is important. It pulls the fat in, puts it into a chylomicron, releases it to the system. The chylomicron is going to drop off the fat where it's needed, and then a lot of it goes to the liver. Again, the liver is very, very important. The liver will take the fat out of the chylomicron, do whatever it needs to do with it, hopefully efflux some of it, and then make a VLDL. VLDL and LDL are our problem children. LDL being the worst because there's far more of them. And then HDL, to review, brings excess cholesterol from wherever in the body back to the liver. That's showing you a chylomicron attaching with this receptor to drop fat off at the adipose tissue. It typically drops it off either at the fat as storage or to your muscle to be used for energy. And your muscle will store a certain amount of fat just for later use. Most of your muscle functions through glycogen, but if you go into fatty acid oxidation, it will use fat cells for energy. Then the VLDL, because the chylomicron became that, will drop off more fat, send more to the liver, et cetera, et cetera. It becomes an LDL with an ApoB by way of an IDL, of course, which is very transient. That's why we don't talk about it much. And then the LDL actually interacts with HDL. The VLDL interacts with HDL, and they kind of transfer different little apoproteins, and they transfer cholesterol. And the LDL will take what's not needed, send it back to the liver, hopefully send it to the intestine and bile and get rid of it. And these are just pictographs of what we've talked about. So your LDL loses a triglycerides and becomes an HDL. IDL has more cholesterol, less triglycerides, and becomes an LDL. You just don't want a lot of LDLs with ApoB because that's what gets into the arterial cell wall. Okay, the LDL molecule is about, I think, 50% triglycerides, so most of it's going to be cholesterol inside. It's got the ApoB 100, the ApoB-C that used to be on, or the ApoC, and the ApoE that were on it get returned to HDL. Remember I said it could transfer? And the LDL's job is to bring cholesterol to the tissues or to bring it back from the tissues when it's not needed. This is all about balance. Your body wants a balance. If you have too much LDL in the serum, because you're either making too much cholesterol or you're not absorbing enough cholesterol out of the serum, it gets stuck in artery walls. We already talked about the APOs. Most mammals have a much better ability to get rid of excess cholesterol than do we. This is why a lot of studies have been skewed when we look at animal studies, and why humans have heart attacks, but like dolphins and apes don't. Even if they're eating, well, gorillas don't really eat meat, but mammals that eat meat or cholesterol don't seem to have heart attacks or heart disease because they can just efflux it. Remember the difference between the rabbits and the rats and the dogs before that sort of slowed down the science for so long? Efflux matters. What happened? What's that? Okay, so in humans, if you have too much cholesterol in your cell, before it begins to crystallize, your body should sense it, trigger some formation of certain proteins to get it to what used to be called reverse cholesterol transport, kind of a historic term, should trigger the proteins to get it back to HDL to efflux it out. That doesn't happen all the time. Quickly, we talked about statins, but you may have heard of a PCSK9 inhibitor. Some of you may be on it. I think the brand, Repatha is the brand name, Repatha. Super, super expensive. That's why most people aren't on it. It's hard to explain. What this does is it inhibits a protein that normally destroys LDL receptors. So when you're on a PCSK9 inhibitor, your body's able to make more LDL receptors. What does that mean? You can pull more LDL out of the serum, get it back to the liver where it's needed, and then get rid of it. That's why these things work so well, and they have almost no side effects. PCSK9, that's the enzyme, way too hard to pronounce, degrades LDL receptors normally. They discovered this because they found that people that had a gain of function of this enzyme had really high levels of LDL particle counts, and people with a genetic loss of function of this enzyme had really low LDL particle counts. So, drug companies said, why don't we induce a loss of function? They did. It works. It works great, actually. And now we've got these inhibitors, these antibodies. So it's an injection. So you get really low LDL serum counts. So what is low? What should your numbers be? Here's a list for you. Nowadays, we think triglycerides should be less than 130. VLDL, sometimes measured, sometimes not, should be less than 15. If you can get your ApoB checked, which you really should be less than 100. But if you're on a statin, the therapeutic goal is even lower, 65 to 80. Apo capital A, a marker of your HDL, should be somewhere between 100 and 200. LDL cholesterol, not the ApoB now, the cholesterol level should be less than 100, near optimal, or what's normal now, 100 to 130. Remember, it used to be 280. And your HDL should be 60 or more. That's all optimal nowadays. And actually, LDL, if you're on a statin, I think they're shooting for 70 now. So those are the numbers you want. So just real quickly, I'll tell you a few supplements that could potentially help with these problems. But honestly, I think statins, if you need to be on a statin, you probably should be on a statin. The biggest side effect being muscle pain. And I'll tell you something you can take to help with that, which isn't here in this slide. But the one thing we have a gummy with CoQ10. CoQ10 is also downregulated when you're on a statin, and it's hugely important for mitochondrial function. So people will get muscle pain. If you take CoQ10 when you're on a statin, it helps. So all of my patients, that take a statin that have achy, really joint pain too, I put them on the CoQ10 to help. Berberine acts like metformin. It'll help modify the level of glucose in your blood and keep it more normal. That reduces inflammation. That reduces the chance of getting oxidized LDL. We have a liver complex. It's like a 2-week course that you take. I do it twice a year just to clean up the liver and get the liver functioning as good as possible. Because remember, the liver is really important in all of this transport and moving around. Resveratrol has been shown to reduce the production of LDL and also to help lower levels of serum LDL. So resveratrol is one of our longevity molecules, and we think it extends life. That's been shown in animal studies and like preclinical basic science work with like worms and stuff. So resveratrol is a longevity molecule. One of the ways it acts is to help control LDL in your cholesterol, in your blood. Omega-3s have now been proven, specifically EPA and some of the studies, to reduce the risk of heart disease. So a lot of people on a statin are offered an omega-3 as well because it dramatically helps to lower triglyceride levels, helps reduce the need for all that transport and the conversion into LDLs, and helps drop LDL levels too. But really, omega-3 functions to drop triglyceride levels. Very, very important. And then the nervous system multi, that is a great supplement we designed and curated that has resveratrol and omega-3 in it, along with some other things that are really, really good for brain health. But those two ingredients really help to optimize your cardiovascular condition as well.
Somebody asked if we could watch this again.
Yeah, all of these are, you can get them, any of these talks, you can get them anytime you want on the websites. So the welltheory.com or warnerorthopedics.com. Is it on the Healing Soul? And on the healingsoul.com.
For those that don't know what the well theory is.
The well theory is my line of natural medicine, or not medicine, I guess the wrong term, natural supplements to optimize our health. And really, my focus is reduction of inflammation, reduction of chronic oxidative stress, and then really just promotion of normal cellular health. And these are just part of that series.
I had the book on.
Also, I wrote a book called Bone on Bone, an orthopedic surgeon's guide to how to avoid surgery, and I talk about all of this in that as well. Hopefully that gave you a basic understanding of cholesterol. It's really complicated. I didn't get into a lot of it, but I think maybe now you'll understand why the levels are being checked, what it means, how you can modify it, and why statins, maybe you should consider them if your doctor's offered them.